Hello guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're tackling a transient problem, that is a problem that we don't have steady state, we don't have steady flow, but we have an initial condition, a situation that happens during a certain amount of time, and then a final condition in which we need to account that amount of time to be able to evaluate changes in energy and changes in mass. So problem statement reads like so. A rigid tank is connected to a pipe by a valve. The tank has a volume of 1 meter cubed, and it initially contains air at 150 kilopascals and 27 degrees Celsius. The air in the pipe has a pressure of 750 kilopascals and a temperature of 27 degrees Celsius. The tank is uninsulated. The valve is opened and left open until the tank reaches pressure equilibrium with the air in the pipe and the air in the tank reaches 27 degrees Celsius. Determine the mass of the air that has entered the tank and the heat transfer during the process, assuming that the air enters the tank with negligible velocity. So let's do a quick description of what's happening. We have a little tank, and it has some air inside. And then we have a pipe. Let's put a little valve here. And then we have a pipe, and this pipe can be very, very long, maybe connected, or maybe it goes like so, it doesn't matter. Okay. And then we know some information about the air inside this pipe. We know some information about the air in here. But then what happens is we open this valve up, we allow some of the air to mix, and then we close the valve again once equilibrium has been reached. Okay, so a lot of important things in the description. First, we have a rigid tank, so we can assume this air, the pressure, the internal pressure this air is imposing in this tank is not going to be enough to change the volume of the tank. Again, air, it's important when we have air because we know that air can be approximated to an ideal gas. So air, we can approximate to ideal gas, and that means we can use, obviously, ideal gas equations, which simplifies our lives. What else? The inner pipe pressure is there, the temperature is, so this is obviously very, very important because this is giving you a very big hint that we're going to have to calculate Q, right, whether it's going in or going out of the tank. The valve is open and left open until the tank reaches a pressure equilibrium in the air. So this gives us an important indication on when this process is going to end, right? So it's going to end when the tank reaches pressure equilibrium with the air in the pipe. Okay, and then determine the mass, and in the tank we can assume the velocity at which the air enters or leaves the pipe as negligible. Okay, so we don't need to account for, that means that all the kinetic energy that we might need to worry about, we don't have to worry about it, it's negligible, okay, consider it zero. Okay, it's not nil, let's just put it tends to zero. Tends to zero. Cool. All right. Now the other thing I'm going to do before we start, okay, so in case you want to do before I do, you want to solve before I do here, is we're assuming properties of air are constant and at 300 Kelvin. Okay, this is not explicitly said, but because we're dealing with an ideal gas, and because this problem does not assume we're going to use any property tables, we can go ahead and use Cp and Cv at 300 Kelvin. If you don't want to do that, well, you're welcome to use property tables as well. But instead of grabbing, when I grab internal energy and enthalpy, instead of doing the way I do, using these guys here, you can just use the property tables. And if you guys need help with that, leave it down in the comments, and then we can do it together later and actually compare with this one. Okay, but now I drew some situations here, and I want to talk about what's going to happen. So this is the initial situation, okay? So I just drew a little bit of the pipe, but pretend this is very, very long. So we have some air inside of the tank. We know some things about this fluid. We know that the pressure is 150. We know the volume of this tank is 1 meters cubed. So we know that the whole space is being filled by air, and we know the temperature is 300 Kelvin. We also know the pressure on the pipe and the temperature on the pipe. Okay, so we have this little valve, and I'm going to open it up. Right when I open it up, so know that I've opened it. When I open it up, I know that air is going to flow from the pipe into the tank. How do I know that? Because I know that pressure on the pipe is greater than pressure on the tank, pressure 1, right? We have 750 here, and we have 150 over here. So what's happening is that we have an expansion of this air into here, and as it's expanding inside the tank, it's compressing the air that was here beforehand, right? And then this is going to happen until we reach pressure equilibrium, and then we're going to close the valve back again. And when that happens, well, nothing changed within this tank. We're going to still have that 1 meter cubed volume. So that is still the same volume. The problem statement says that our temperature is 27 degrees Celsius, right? So if you look at these three states, this is what this is what I'm going to call my first state. So state 1. This is going to be my second state, state 2, and this is going to be our transient state. Okay, so this another way to label this is our initial state here, our final state over here, and then our transient state there. Okay, what is happening if we think about energy balance? Okay, let's consider the control volume to be the tank. So we're only interested in the tank now. So what would be our energy balance look like? Think about it this way. Let me go ahead and let me copy these. Let's do it down here. Yep, down here works. Okay, now let me remove whatever is not our control volume. And let's go ahead and think about what's happening in terms of energy. Okay, so on my initial state, I have the pressure and the temperature, and I know the volume of the tank. So it's fairly easy for me to grab information for this state here. We know this is 150 kilopascals, and we know it is at 300 Kelvin, correct? On this state here, we know the temperature because the temperature was given, and we also know it reaches pressure equilibrium with the pipe, which was at 750, right? So remember that because of that special sentence that says that this process is only going to end once we reach pressure equilibrium, then we're safe to say that this here is at 750 kilopascals, right? Which is the same pressure of the pipe. And then obviously, assuming this is the tank is not, not going to make any, not going to take away much of the gas in the pipe, which is generally the case, then the pressure is going to be the same as the initial one in the pipe, which is 750. Cool. Now, what about the middle part, the transient part? So on this transient part here, we have a couple of things happening in terms of energy, right? Well, we have that air going in that we said before, and as that air is going in, because there's some mass of air going in, so there's an internal energy related to that, but there's also the flow energy, which is related to pressure times volume, right? So as we talked about, it needs to expand and push the air that was there initially, so it can compress it. So we have flow energy as well, and because we have both internal energy and flow energy, then we're going to consider here the enthalpy, right? And this is enthalpy going in. But because we generally get enthalpy in terms of specific enthalpy, in terms of kilogram, I also want to multiply that by the mass going in, right? Another way to think of this is we could have, said, oh, there's some energy going in, my uppercase enthalpy. This is what going in, right? And the energy going in, I can break that down into the specific enthalpy and the mass times the mass going in, right? Same thing. But we also know this is not insulated, right? This is a not insulated tank, so we most likely will have Q going in or out. Okay, and when we have a situation in which we're not sure what's happening, what we can do is we can always assume it's going in, and then we're going to correct that later, because if our assumption was incorrect, then we're going to get a negative value. So you're welcome to do that. The other option is to actually think about what's happening and try to understand the problem beforehand, and that's going to give you not only a better understanding of the problem as a whole, but also a better understanding on the thermodynamic properties and what we're trying to achieve. Okay, so think with me. If we're doing an energy balance, so my energy, we cannot create or destroy energy. Right? Looking at this scenario here, we have energy going into our tank, right? Only think about this for now. So that means that whatever energy I have, let's just put E for energy, okay? Whatever energy I have on state 1, okay, plus whatever energy went inside, that's enthalpy in, will be equal to my energy on state 2. Correct? Because we have energy going in. So this means that this guy here has to have more energy than the initial state there. Right? So if that's true, and we're dealing with an ideal gas, then that would imply, let me remove all of this, that would imply that my second state, the internal energy of my second state, would be greater than the internal energy of my first state. Right? But because this is an ideal gas, we know that on ideal gases, the internal energy is only a function of temperature. And it's quite clear from the beginning that the temperature on both states are the same. So that means because, we can put it this way, because T1 equals T2, then, and because it's an ideal gas, then U1 equals U2. Right? And if U1 equals U2, then the only way this can happen is if my Q is removing energy from this tank. So we cannot be giving energy to this tank, or else we will not satisfy this idea. Because if it were giving energy to the tank, we would have the energy from the heat plus the energy from the enthalpy. And that would imply that this guy could not be 300 Kelvin, right? So that tells me beforehand that Q has to be leaving this tank. So if you do this kind of analysis beforehand, that's a way to not only train your understanding of the subject, but also it facilitates your life, because now I can write the energy balance, and I can also say, well, if this is the case, then the energy in state 2, for this to be true, I need to rewrite the whole thing as being, okay, energy on state 2 has to be whatever was there to start with. Let me just push this to this left. Whatever was there to start with, which is this guy, plus whatever went in, minus whatever came out, right? So the way that we would write this energy balance, let's say in a more elegant way, would be the energy on state 2, which is a closed state, it's a closed system, so energy on state 2 is just my internal energy. And I can do, once again, I can have this uppercase U, or I can have this written as lowercase u times the mass. It has to be equal to the original one, so internal energy 1 times the mass 1, plus whatever went in, and that is my enthalpy in times the mass that went into my system, minus the leaving of the heat, right? And again, like I said, if you don't want to do this analysis beforehand, you can assume the energy is going in, not going out. And then by the end of it, if you get a negative number, it means your assumption was incorrect and it's indeed going out. Okay, if you do the assumption beforehand, if you do the analysis beforehand and you know that this is going to be leaving the system, then this is going to give you a positive number by the end, and just confirming what you said. All right, cool. So what do we need to be able to solve this? We need the masses, and we need the internal energy and the enthalpy, and then we can solve for Q, all right? But if we go back here and we look at what's happening in terms of mass, we have Q is not, this guy here is not transporting any mass, right? This is only energy. The only mass that's changing is this mass in. So if I do now a mass balance, right? So if I do a mass balance, so I can't create or destroy mass, my delta M has to be 0, then that means that my final state, this one here, has to be equal to the original mass that I had here, plus whatever went in on the transient state, right? So that means that my mass on the second state is equal to my mass on the first state plus whatever mass went in. And from this point on, then we can start to think about, trying to find some of these unknowns. So then we can plug into here, and then we can find the heat that left this system. All right. So this is an ideal gas. We have everything we need to be able to find the mass with on the first state. We have everything we need to find the mass on the second state. We can do that fairly easily. Let's go ahead and do that. So for state 1, remember that ideal gas means that PV equals mRT. This M can be for mass or for number of moles, depending on the unit you're using for your R. So if I'm doing for state 1 and I want to find a mass, I just have to do pressure 1 times volume 1 divided by R and T1. We have all that information. This is 150 kilopascals. Let me put the units on the side there. 1 meter cubed. This is 287 at 300 Kelvin, and this is 300 Kelvin. Okay, unit-wise, quickly, kilopascals times meters cubed. This already gives us kilojoules, divided by kilojoules per kilogram Kelvin, and this is Kelvin. So note how kilojoules and kilojoules go away, Kelvin and Kelvin go away, and I have kilogram dividing, which is going to be my unit there for the mass, which makes total sense. And this is, what did I get? 1.742 kilograms. Okay, so this is a mass on state 1. What about state 2? Well, exactly the same thing, except our pressure is now 750. Everything else is exactly the same, including the temperature. Okay, units are going to be the same as well, obviously, and this is about 8.711. Cool. And now from here, it's quite easy to solve the first part of the problem, which is how much mass went in, because if we have these two fellows here, and we know that there's this relationship here, then that means that my mass in is simply my mass 2 minus my mass 1, which is the 8 minus the 1, and that gives me precisely 6.967. 69, sorry. You can approximate that to 6.97 if you wish. 100% okay. So that's the first part of the answer. And the second part wants to know what was the heat that entered or left the system. We already concluded it's leaving the system, so now all we need to do is actually solve for this. Well, one thing that you might know is that we don't have U2s and U1s and H-ins. We can find that, but we don't really need to beforehand if you don't want to, because I'm going to show you something. If I'm solving for Q, my Q will be sending that way positive, so I'm going to have U1 m1 minus u2 m2 plus mass in h in. Okay, now I can, where I have my u1 will be equal to u2 because of the temperatures, right? We talked about how temperatures are going to be the same, so therefore they're the same thing. So this is, in reality, I can rewrite this as, sorry, let me just put it here. I can rewrite this as u, that's m1 minus m2 plus mass in times h in. Yep. Now, if you note, this guy is just negative mass in, right? Mass in is just m2 minus m1. So that blue guy there is just negative mass in. So I can rewrite this as, this can be my enthalpy going in minus my internal energy, doesn't matter if it's 1 or 2, they're the same, times mass in, right? The difference between the enthalpy and the internal energy for this ideal gas here will be R. Why is that? Because my enthalpy is my Cp times my temperature. My internal energy is my Cv times my temperature. Okay? The difference between Cp and Cv is R. You don't have to do that if you don't want to. I'm just simplifying things. You could have calculated beforehand, just plug in Cp and Cv. These guys, if you recall, this is 1.005 for air at 300 Kelvin, and this is 0.718. So I can rewrite this once again as, Cp minus Cv. The temperature is the same for both, so temperature, mass in. Yeah, and now we have everything we need. This is the same thing as R. You can do it for yourselves. You can just take this guy, subtract this one. You're going to get 0.287, the same R that we used in the beginning. This is 300 we knew from the start, and this we found out to be 6.97 approximately. Right, so let's go ahead and rewrite that. So 300 and 6.969. Okay, unit-wise, this guy is kilojoules per kilograms per Kelvin. This guy is Kelvin, and this guy is kilograms. So we're left with kilojoules, which makes perfect sense because we're calculating heat, and it's a form of energy, so all good. So my conclusion here is that Q is, what did I get? About 600 approximately. Yep, and I got a positive number, which means that my assumption was 100% correct. It is indeed leaving the tank. Okay, so we can put a little. All right, so that does it for this problem in terms of solving. What I encourage you to do is, if you don't like doing this analysis here, right, to understand or if you find this too complicated, go ahead and put the energy, assume it's going in, so we're going to invert that, and then obviously by the end of it you're going to get a negative number here, which is going to tell you mathematically that the heat is leaving, not going inside the system. Okay. The other thing that I want to point out before we finish off is that obviously when I'm doing this analysis here, where's my energy balance? When I'm doing this analysis here, okay, I'm already ignoring all the other forms of energy. So I'm ignoring work. There was no mention to work. There was no mention to the kinetic energy when you was negligible, so you can approximate that to 0. So the other option you have is to actually write the whole thing down. You can write the whole, put it down here, the whole sum of mass 2 times gravity z2 plus velocity 2 squared over 2 plus u2 minus m1 gravity height velocity u1 has to be equal to any changes, right? The q or the work, if we had any work, the any mass going in, which would increase the energy. So again, this same thing, gz in, velocity of what's going in divided by 2, enthalpy of what's going in because it's a flow, minus whatever's going out, right? Mass out, g height of the thing that's going out, the velocity of whatever's going out squared, and the enthalpy of whatever's going out. Right, so you could write this whole thing, sum of everything. This is like the general equation. But if you're comfortable with this, what we did is, well, there's nothing going out whatsoever, so this mass is nil, so this whole thing goes away. There is no work being done whatsoever. I should say no boundary work or no external work, I should say, because we know the gas is doing work to expand, and the one that was inside is being compressed. So there's no mention to any potential energy or differences in height that would justify accounting for these. It clearly says that the velocity is negligible, so all these guys go away. become nil. And what else? And that's it, right? So if you look at what ends up happening is that we have the mass on the second state, internal energy in the second state, the mass on the first state, internal energy in the first state, the heat going in or out, and then the mass going in and the enthalpy going in. So we end up with the same thing. It's whatever you prefer, whatever you feel more comfortable with. You can memorize this whole thing and try to carry it on every single time, or you can just pay attention to what's happening and try to put down the energy balance. The only problem with doing it straight like that is that you might end up forgetting something. Yeah, but if you do a little drawing, if you know what you're doing, it's not going to be a big deal. Hope this helps. If you have any questions, drop them down below. If you like this video, if it helped you out, please give it a like and subscribe to the channel so you're always up to date with our latest problem solving tips and theory.